Welcome back to part 2 of our video on text-to-image generation. We'll talk about something called diffusion, which powers systems like Imagine and DALL-E 2. Last time, we talked about how you could represent images as visual words, and then use a large language model to generate new images. This is the idea behind the Parti system from Google. Another approach is to create a program that generates images and modify that program to use language. This is what Imagine does, another text-to-image system from Google. How does an image generator work? Well, suppose I asked you to generate 100 new images. How would you do it? The simplest way is to just choose a random value for each pixel. That produces noise patterns like this. It's like what you see on your TV when you tune into the wrong channel. Now suppose I asked you to create 100 images of raspberries. That's a lot harder. Conceptually, you can think of two distributions, random images and raspberry images. Each point here represents an image. Random images are easy to generate. Raspberry images are hard. But suppose we had a magical way to turn random images into raspberry images. This is what diffusion does. It's a method for transforming one distribution into another. How does this work? Well, it's pretty hard to turn a random image into a raspberry image, but it's relatively easy to go the other way. We just need to add more and more noise until the pixels become totally random. You can think of the animation I just showed as a path through the space of images, where each frame is a single step towards more randomness. Now, what if we played this animation in reverse? This defines a path from a random image to a raspberry image. And if we repeat this with another raspberry image, we get another path, which we can reverse in the same way. So with lots of raspberry images, we get many of these paths. And we can use them to train a neural network to predict all of these arrows. Now we can use this trained network to generate new raspberry images. Here's how. Let's start with the random image, represented by this point. If we feed it into the diffusion neural network, it outputs an arrow. If we now step along this arrow and feed the new point back into the network, we get a second step, and so on. Great! Now we have a neural network that can help us generate raspberry images. But what if we want apples? Or peaches, or mangoes? We could train a different diffusion network for each of these, but there's a better solution. Let's train a single diffusion network that takes the name of the fruit as input. So if we specify apple, it gives us this vector, but mango outputs a different vector. This is called conditioning the network. What we really want is to condition on phrases or sentences. For example, this sounds a bit like a fruity dish, but it's actually a type of hat. Here the word raspberry refers instead to the color of the hat. To capture this level of subtlety, we need a language model. Now when we prompt with raspberry beret, the language model converts these words into a knowledge representation which guides the diffusion model. And that, in a nutshell, is how Imagine works. Let's try some examples. Here are a couple of raspberry berets generated by Imagine. And for fun, let's try this instead, beret of raspberries. Now it's a hat that's made out of actual raspberries. And here's another one. I love how it worked in the leaves of the raspberry plant into the hat on the right. And here's some chocolate guacamole pancakes. They look a little bit different from the real ones I made in the large language models video. And here's our squirrel from part 1 inside a nutshell. You may have heard of DALL-E 2. This is a popular text-to-image system by OpenAI. DALL-E 2 was released before Parti and Imagine, but you can think of it as a hybrid of these two systems. DALL-E 2 augments a language model with visual words, like Parti, but like Imagine, it uses diffusion to decode the resulting visual words into an image. Instead of representing an image using a grid of patches, DALL-E 2 encodes the image as a long vector of numbers, known as a clip embedding. This more abstract visual word representation enables some cool capabilities. For example, DALL-E 2 can take an image like this, encode it as a vector of visual words, and then use these words to condition a diffusion model to generate a new image with a similar style. Very cool. Here's another example, in DALL-E 2's version. If you look closely, you can see some weird stuff going on. These methods do make some rather intriguing mistakes. Here Partee put a live squirrel into the latte. And in this example, Imagine put the avocado on the bear's nose rather than in the pancakes. They're not good at counting. This result is pretty typical. And they really struggled spatial relations. Partee consistently swaps the left to right order for this prompt. These systems are also susceptible to bias, producing inappropriate results for some queries. This continues to be a challenge for these and other state-of-the-art AI systems. I hope you've enjoyed this video on text-to-image systems.